This is part 12 in a series of videos in which I'm attempting to repair and restore a MADAS vintage mechanical calculator. This particular calculator is motor driven, and unfortunately the motor had developed some fairly serious leakage to ground through the rotor shaft, and so I tried various things, but the only solution in the end is to rewind it. The stator seems fine, the field coils are fine, they're not leaking, the insulation still seems good, but I was getting very high leakage on the rotor, and it was getting worse the longer the motor ran. Now, because I don't have any technical information on this particular motor, I needed to go through the fairly painstaking process of unwinding it so I could figure out exactly how it was wound. It's a series wound motor, so that in theory it should be wound to a fairly standard pattern, but I needed to figure out what the timing was of the commutator contacts to the rotor slots. So there are 24 contacts on the commutator, 12 slots on the rotor, so in theory there should be 2 windings per slot. And when I say slot, I mean the wire goes down one slot, comes back up a different slot. They're not adjacent, and they'll be spaced out such that they're in pairs, one either side of the rotor. And so what I did is soak this in solvents for a while to soften the black gunk that was holding it all together. And once all the wires had become reasonably free, I could then start to try and examine it and see how it was wound. Unfortunately, I couldn't do that by just looking. It was too dirty and convoluted in the way it was actually wound. Turns out this has been wound in a bit of an unusual fashion. Now, in terms of the slots and the connections, it seems to be fairly standard. It's just a relatively non-standard way in which the individual coils have been put on in terms of the order they were wound onto the rotor. So once I'd figured that out, it became clearer as to how it was wound, and what I've ended up with by unwinding it is a nice collection of old wire and a winding list. So just to check that my theory is right on how this is wound and make sure I fully understand this, we'll have a look at the results of unwinding it and the notes I took, and make sure that the assumptions I've made are correct for this rotor. And then we'll do a quick leakage test as we did before to make sure that we don't have any leakage still on the commutator. Still needs cleaning up quite a bit. I've removed a lot of the old insulation and gunk, and we've now got these nice end pieces. I don't want to take the commutator off if I don't have to. It's cleaning up fairly well, and I'm hoping I'll be able to just finish cleaning this as it is, reapply new insulation, and then start rewinding it. Examining this fairly closely, it became clear why it was starting to cause a problem. What can happen with these when they start to corrode is the core is made up from a stack of laminations, and if they start to get corrosion on the surface, the corrosion takes up more space than the original coating on the metal plate, and so the core starts to expand. And that's what started to happen here on several of the windings, or several parts of the core. It's really started to expand, and it's about 1 millimeter wider at the outside than it is at the center. And because the coils are wound on here fairly tight and they're impregnated to make them, to all intents and purposes, solid, what happens when this starts to happen, it puts a lot of force on the wires, and it can cause them to start shorting out. This one was acting a bit strangely in that it was the leakage in one direction was far greater than in the other, so it's acting like a diode, but I think that's just the nature of the material that was being used. So what I've done is finished unwinding it. I need to clean this. I've cleaned up the commutator. The wire was actually soldered into slots on the inner edge of the commutator, so that's quite convenient for us. It makes it very easy to remove them and then reattach them. As I say, we'll do a quick leakage test on this in a minute to make sure we've resolved the problem, but first we'll look at the notes I took and see if what I intend to do in terms of rewinding it would be correct. Okay, so if this rotor was wound in the way I would expect it to be, then the coils will be laid down in pairs, so there'd be a coil running from a slot, for example, from here round to here, and then a matching coil on the opposite side running from here to here, and they would be wired onto adjacent contacts on the commutator. It's kind of a bit counterintuitive, but when you work out how this would give connections when you put a brush at either side of the commutator, it starts to make sense. This is slightly unusual in that rather than the coils being laid down and progressing smoothly around the core or the rotor, even though the contacts were progressing smoothly and consistently around the commutator, the windings weren't laid down like this. There was a pair of windings here, for example, and then offset by quite a large amount, another pair of windings, and offset again, another pair of windings. But looking at the connections, it does appear that it's still wired such that the result is windings progressing consistently around the rotor, which they kind of have to, otherwise the motor won't work. So what I've ended up with is a list of the windings. Now, of course, this is reversed, so when I come to rewind this, for example, we have a winding here that says it went from 7 to 8, then from 8 to 9, because there are 2 coils per slot. So we go from, for example, this commutator segment round the slot with 100 turns. It's terminated onto the next segment of the commutator, and then another 100 turns in the same slot on the rotor, and then that's terminated on the next commutator segment. So we end up with effectively 2 coils connected to 3 commutator segments for each slot. So when I rewind this, I need to go from commutator segment 9, wind it round the slot, and that will be a particular slot on the rotor, terminate it at commutator segment 8, and then going from segment 8, wind another 100 turns in the same slot and terminate that on segment 7. So that is going to give me 2 windings per slot, and then there should be a matching winding on the opposite side if we were to count this round. So I drew this out as well, and although the windings do seem to jump around, so I essentially gave the commutator segments numbers and the slots letters, and what you'd normally see is the commutator and slots on the rotor would go up sequentially, so we'd expect to see A, C, etc. So it would jump by 1 each time, and then you'd have B, for example, on the opposite side. So A and B are indeed on the opposite side. That was the first winding that I took off. But I would have expected to see C as the next one, but it's actually C, which was the next winding to be taken off, was actually offset round the rotor. And that's how it progressed all the way along. It kind of jumped around quite a bit. However, if we look at this in terms of a sequence, and we start at A, so this is winding A, and it goes from this rotor slot round to here. And the next one, if we look in terms of going in this direction, so if we imagine we're going clockwise round the rotor, then the next one is G. So we go from A, the next winding is G. If we look on the connection diagram, we see A, the next one's G. And the next one, according to the connections, should be E. So if we go from A, I'm looking at the start point here, we go around to the next, we've got G, we go around to the next, which is this one, we do indeed have E. So it is progressing around correctly. I've checked all of these, and that's exactly how it's actually wired. So the relationship between the commutator segment connections and the actual coils is correct. It's exactly what you'd expect it to be. The only difference is they're not laid down sequentially, they're laid down in kind of an odd pattern, but the actual connections are exactly what we'd expect. I could, if I wanted to, simplify the rewinding of this and just wind it, so I could start with one piece of wire at A, one at B, and then just wind continuously one coil at a time, stepping around one slot every second set of windings. But I've decided, because this is a vintage machine and I want to keep it fairly authentic, I'm actually going to rewind it back in the same way that it was originally. Makes it more complex to rewind, but at least it'll keep it more authentic. So the next thing is to start actually doing the winding. I won't video much of this. It'll take a long time. It's going to take probably 10 hours, 12 hours to rewind this. I'm not going to video all of that. I'll stop now and again and take a few update videos and show the progress as I go. The first step is to finish cleaning it and then to put some insulation onto the core. And before I do that, we'll just do a quick leakage test to make sure that we don't have any leakage left on the commutator. Okay, so for the testing, we'll do exactly the same test as we did previously, and I was getting an increasing amount of leakage doing this test, so the longer I run the motor for, the more it ramped up. Started at 70 milliamps, went down to just a few microamps, and then it started to fairly rapidly increase again. So we were getting several mega ohms between the commutator and the rotor shaft, so we'll start by measuring that. So going from the commutator, I've got this wire wrapped around the commutator again to short all the segments together, and going from that wire to the rotor shaft, I can't really touch it because I'll get a reading, then as you can see we're getting absolutely nothing at all. We'll go to the other end of the shaft and we are making contact with the shaft, so that's looking good. I'll reverse the meter, and again absolutely nothing at all. So it's looking like there is no leakage between the commutator and the shaft, and I did put this in the lathe and tidy up the back end of the commutator segments once I'd removed all the solder from the slots, and I just tidied this up of course. So next thing is we'll hook up the power supplies and apply 120 volts to this and measure the leakage current. So I have the same setup as previously. I've got a couple of power supplies and I've got a current meter up there. So we'll get this hooked up. We'll start off with positive on the commutator. We'll clip the negative to the shaft, and I'll power up the supplies. I'll move the camera so you can see the current meter. So as you can see, almost nothing. I'll turn these supplies off. Now although the current drops, so it's kind of indicating we're getting some leakage, we're actually not. There's no current flowing through this at all. I'll disconnect one of the connections from the rotor, maybe so you can see it. So I've got one of the leads disconnected now. I'll power the supplies back on, and notice we're getting fairly similar apparent leakage test again, and that's just because of the nature of these supplies. As you know from previous videos, they do put out some RF noise, and that's really what we're picking up here. It's just the AC content of that projecting itself around the lab here. But what I'll do now is reverse the connections to the rotor, and we'll check it the other way around. So the supplies are off. We'll now put negative on the commutator. We'll clip positive to the shaft. Power these supplies back on. I'll move the camera back up again. And so as you can see, we're getting exactly the same thing. I'll turn the supplies back off, and as we got the other way around, although it seems like we're getting a change in leakage, I'll disconnect both connections this time. So I now have both of these disconnected, and I'll put these supplies back on. And as you can see, we're getting pretty much the same reading, and that's just because these wires are picking up the RF output from the supplies, but there is no current flowing through the rotor at all, so there's no leakage. Turn the supplies back off. So I'm fairly confident now that this commutator is fine, there's no leakage on it. What I'm going to do is a full pat test on it before I go any further. I'll leave power applied for several hours to make sure that it doesn't start to develop any leakage, and on the assumption that I don't encounter any problems, which I don't really expect to, then I'll start rewinding it, and hopefully we'll be able to recover this motor. Okay, so as you can see, I've cleaned up the rotor. I've cleaned out all the gunk and the insulation that was causing the problems. I've recompressed the core to make them the right shape. It had expanded a little bit, and after I'd cleaned out the corrosion, I could press these back to the correct shape. And I've checked there are no sharp edges. Luckily I do have the two insulation cheeks, so these are to prevent the sharp edges of the metal core from digging through the insulation on the copper wire, and I do have both of these, one for each end. If I didn't, they are quite easy to machine from a sheet of Paxilin or something similar, but luckily I don't need to do that for this, but I will need to put some insulation on the rest of the core. Before I do that, just a quick apology for the long delay between videos. My dog's extremely ill at the moment, so we're just going to have a quick look at her and see how she is. So this is Izzy. Unfortunately she's only been given a couple of weeks, so very sad time. If you're not a dog lover, you probably wonder what all the fuss is about, but for anyone that owns a dog, you'll know it's quite a difficult time. So unfortunately the videos will be few and far between for the next few weeks, and after that hopefully normal service will be resumed. But let's get back on and continue working on the core. Okay, so looking at the core, the first thing I need to do is insulate it so that when the copper wire is wound on, it doesn't bite through and short out onto the iron parts. If it was a bigger motor, we'd use barley paper or fish paper, but it's a bit too stiff for something this small, so I'll be using Kapton tape on this, and as I said, we do have the insulation cheeks at the end, so that will give us quite a good insulated basis for the core. So I get this insulated, we'll have a quick look at it, and then we'll look at the wire that we'll use to rewind it. Okay, so that's the rotor core pretty much insulated. So I'll put some additional insulation around the portions where the windings will be pressed against the shaft, and I just put a couple of bits of tape on to hold these two cheeks on before I start winding. The windings themselves will kind of pull that into place once I start, but that's the core pretty much ready for starting the rewind. Although I've left the tape running across the outer portion of the core, that's mostly to make it easy to wind. It's one piece of tape, and if you're not careful with very thin wire, it's quite easy to get one of the windings between the core and the tape if you're not very careful, and obviously that can cause a short. So I leave it like this until I finish winding, and I trim off the excess and put the plugs in. But we'll look at that in the next video. The last thing I want to do in this video is to have a look at the wire that we'll be using and just check that we've selected the correct size wire. Okay, so you might think it'd just be as easy as taking a piece of the wire we took off and measuring its diameter. Unfortunately, with old wire like this, it's not quite that straightforward. So this is showing a fairly consistent 0.19 millimeters pretty much all the way up and down, but that's not the equivalent to modern enamelled copper wire. The insulation on old wire like this is extremely variable in terms of its thickness, and what we need to know is the diameter of the wire itself. Now, I took an approximation by measuring the end of the wire where it was had been stripped, and we got something around 0.12, but what I tend to do is take a length of the old wire and it's about 4 meters long, so it doesn't really matter how long it is, but just a fairly lengthy part is quite useful. And then I measure the resistance of it. So if we clip that to the adjuvant, it's in ohms mode. Quite difficult to clip on because it's such a thin wire, but I'll find the other end of it. So this piece is about 4 meters long, or just over 4 meters. And so we've got the other end, we'll clip that on, and we're seeing about 4.6 ohms, and that's the original wire. So if we take a piece of the wire we intend to use as a replacement and we measure its resistance for a similar length, we should of course get the same. So I'll take a piece of the wire that I intend to use. So I've cut a piece of the wire to exactly the same length, and again we'll clip it to the adjuvant and measure its resistance. And of course, if it's the right gauge wire, it should be pretty much the same. Okay, so find the other end, clip that on. We had 4.6 before. Let's try and get a good connection. And we're getting 4.7 now, so slightly higher, but certainly within the realms of what's acceptable. There will be variability, of course, in the wire. But just to clarify this, if we go to the next gauge wire thinner, and that is 0.02 millimeters smaller in diameter, it's very difficult to see the difference just by looking at the wire, but this is exactly the same length, so I'll replace this. We'll take the first end, get that clipped on, and the second end. And you can see that's 9.4 ohms. So pretty much double. Even though it's only 1 gauge thinner, we're going to almost double the resistance. So it does make quite a big difference. And if we measure these two wires there, so this one measures about 0.1 millimeters, and the one that we intend to use measures 0.12 millimeters. So 0.02 millimeter difference, but it does make a huge difference in the resistance. So it is worth spending some time making sure we've got the right gauge wire, because it will have a significant impact, and small differences do make a big difference, and it can be quite hard to measure this accurately. So now that I have the right gauge of wire, in the next video what I will do is go through the rewind process, and what I intend to do is wind it back the same way the original motor was wound. It's not the way you would do it with a new motor, but it results in the same electrical winding connections. It's just physically different layout on the rotor itself. So I'll do that in the next video. Comments welcome, but hopefully we're getting fairly close now to having this motor rewound.